Welcome back. Right now we're going to be talking about ideal gases. Remember that for a mass balance, we need mass or number of moles, and these are related through the molecular weight, but we can only measure volume, pressure, temperature, if in a process it is difficult to be measuring mass or number of moles. So we need to relate them. In solids and liquids, which are modeled as incompressible, it is very easy because you have the density. Mass is going to be equal to density times volume at any pressure or temperature. And of course, there are variations, but they are minimum. So that's the reason why we do this. But in a gas, pressure and temperature does matter. And we need equations of a state. The ideal gas equation of a state, which is the one that we're going to talk about right now, is stating that the number of moles equals pressure times volume over RT, where T has to be in Kelvin or Rankine, it has to be absolute. Pressure has also to be absolute. It cannot be a gauge pressure. And the R is the ideal gas constant, which has a value of 8.314 Pascal cubic meter per mole Kelvin, or 0.082 liter atmosphere per mole Kelvin. And there are some devices that are using standard conditions. The standard conditions is when the temperature is 0 degrees Celsius, which means 273 Kelvin, and a pressure of 1 atmosphere. And if we want the volume that 1 mole of an ideal gas is having, well, we can solve for the volume, which is nRT over P, plug the numbers, and we're going to find that 1 mole is going to be 22.4 liters at the standard conditions, and or 0.0224 cubic meters at the standard condition. And this is for any ideal gas. For a closed system with no chemical reaction, where we have two states, let's say we have a process, we have a piston with a gas, and then the volume increases, so the state has changed. Pressure 1, volume 1, temperature 1 is going to be equal to pressure 2, volume 2, temperature 2, which means that if we are changing volume, probably pressure is also being changed, temperature is also being changed. When we have mixtures of ideal gases, Dalton's law will state that the total pressure of the mixture is given by the sum of each contribution of each component. And each component will have what we call the partial pressure. So if we have, I don't know, 3 components, well, each component will generate its own pressure, which is the partial pressure, and the sum of that will be the total pressure. For the ideal gas, that partial pressure is going to be equal to the mole fraction times the total pressure. Or in other words, if we want to solve for the mole fraction is the pressure of the component over the total pressure. And Amagat's law states something very similar, that the total volume of the mixture is given by the sum of the contribution of each component of the mixture, which means that each component will have its own volume, which is the partial volume, and the sum of all the partial volumes will yield to the complete volume. This is ideal gas mixture. It is very important for you to understand that this is a very special and very complicated situation. So not always the volumes are additive, which means that this is not always applying in mixtures. For the ideal gas, the volume is equal to, the partial volume is equal to this molar fraction times the total volume, or in other words, once again, we can calculate the mole fraction as the volume fraction. In this case, in ideal gas mixtures, it is the same.